forget anything. All right. Okay. So what I'm going to take you now to the second part of the course is the modules that's talking about oscillations and waves. And the good thing about this one is, to me, this module is going to be the easiest of the course. I mean, the level of difficulty is down a little bit because, first of all, I don't think you need a lot of calculus as compared to the first module, even though we didn't have much anyway, but this one is even less, okay? And second thing is, I think it's very, I mean, sort of like bring you guys back to mechanics because this part is a mechanical thing. So the imagination is a little less. So you can pretty much use your everyday lives experience to sort of like understand the situation better. So you don't have to imagine or visualize like molecules, atoms, things traveling like crazily in the system on and on. So no. So this one comes back to Newtonian physics again. However, the very good thing about this one is we'll have a very, very interesting mathematics that's describing the oscillation. Okay. And eventually, when this oscillation is coupled to something else, so this means you allow interactions to get into your picture, then you start to generate something that can propagate through the space or whatever things that you try to look at, and it generates waves. So this is the reason why we connect these two topics together, is oscillations and waves. Because every time that we talk about waves, I mean, the source usually is something oscillating. So first, what we are going to learn today is we're going to learn how to describe the oscillations motion. So this is a kind of motion. And I think you probably have seen this word before. It's a simple harmonic motion. And I'm going to have a chance to describe to you one more time. What does it mean? For those of you that didn't care before, or it's just like for those of you that's like, okay, I hate physics already, so yeah, you don't have to dive too deep. Everything is bad. Okay, so that's what I'm going to sort of like sell you this stuff. It's very interesting, and I hope you buy it. I think you're gonna buy it. All right, and once we get to that, and then we'll have a chance to talk about the waves, all right, and the connections between the two, and then we're gonna have like an example that we can study waves very thoroughly. And I think this is the one that you're gonna see the mathematics like put into work. It's a waves on strings. Okay, and once again, it's just like use gas to study thermodynamics. Strings here will be used to study waves, something like this. So we just pick a system that is so easy to use, easy to picture, easy to understand, and then the property is not too complicated, and then you can use this as your system, okay, for study. All right, so that's what the point of why. I mean, those of you that keep asking like why, it's just like humans are smart, I think. So physicists in the past, they're smart. They know how to pick a good things to study or something like that. Right? I mean, that's my answer. Okay. All right. Please don't go quantum. Okay. No, that's not in the course description. So don't worry about it. For those of you that really want quantum physics, I think you have to enroll for physics 3. I don't know if there is physics 3 or not, but that's not in this course. All right. So don't worry about that. Okay. All right. Let's dive into it, guys. Let's look at the first slide right here. How do you feel? All right. So just read it first. Don't panic. All right. Don't shy away from it, guys. It looks like, even though like Ajahn, you said no calculus. No. I mean, we cannot avoid calculus, but I'm going to explain to you, it's not that bad. All right, let's take a look at this. If I'm asking you, all right, let's look at one system. All right, just focus on a system first. You have a simple system as a single mass, and there is a spring attached to it. Okay, and everyone still remember, every time you have a spring, we have a simple spring that follows Hooke's law. F of the spring is equal to some constant multiplied by the x, and the x is just the position of the spring relative to the equilibrium point. So when I say equilibrium point, mean spring usually it has its own length, but then if you apply some force to it, you can stretch the spring or you can compress down the spring. That X is that position right there. For example, in the first figure right here, X is the position of the spring that is already being stretched, right? So it's extended out. So X is the size of the, you can think of like it's the length that has been changed from the equilibrium point of the untouched spring. Okay, sounds good. All right, so you can call it like a displacement. Okay, and just to make this thing a vector equation, so actually what I can do is I can say, hey, this is vector, and I can put the negative sign to it, so X can be vector as well. When I say X can be vector, is just now instead of just saying that it's a position, you can say it's a displacement. So that's the X vector. With me, guys? So that means X contains positive or negative value. So look at the bottom one, for example. This one right here, X is negative. The good thing about writing the equation in the vector format is it has the sign associated with it. For example, in the first figure, the figure A over here, X is positive because it's being stretched. Okay, so X is positive. With the negative sign in the front, that means the force due to the spring will point in the negative X direction. You guys with me? And that is this blue arrow right here. So it's going to be opposite direction to the green arrow that representing the displacement. Okay, yeah, with me? All right, that's a good thing about having the vector equation. So down here, I can do it one more time. So look at this one. When the spring is being compressed, the displacement vector is going to point to your left. With the equation that has a negative sign in the front, your spring force will point to the right. Okay, so that's just a quick reminder of what is going on with the mass on spring system. You can use the equation of motion. You can draw and you can write the equation of motion using Newton's law. That's it, guys. So if I'm asking you, hey guys, can you write the equation of motion? Equation of motion is the equation that is going to describe the motion of this mass. You say, well, no problem. Let's go Newton's second law, sigma F equal to ma. Yeah. What else can you do? Right? It's a Newtonian physics. However, if you look at this mass, so now I'm going to do a free body diagram right here. When I say free body diagram, means just imagine that you are looking at just a single mass. This is your sort of like the mass that under your condition, under your consideration right now. So what are the forces acting on this mass? You probably say, well, Ajahn, according to Newtonian physics, there will be mg pulling down, there will be normal force pointing up, and that force due to the spring is being applied. So let me redraw that vector again down here. So that is the spring force. Sounds good? All right. However, the thing is, well, Ajahn, you don't have to worry about the N and the mg because they're going to cancel each other out. All of the motion that is happening is going to happen along the x-axis. So this is going to be a single one-dimensional motion. Everything is going to move along the x-axis alone. So you don't have to worry about the N, you don't have to worry about the mg because it's perpendicular. So everything is already in the 90-degree angle with it. They're all independent, so you don't have to worry about it. Just forget about everything is going on in the y-axis. So this is it. So from the look of it, that's only single force acting on this mass, and it's just a spring force. And that's it. From sigma F equal to ma, the force is negative kx because it's pointing to the left, and just equate that to m times the acceleration of the mass. You guys good with this? Maybe I spend too much time describing this, but I hope you get the point of applying this Newton's second law and get to the equation of motion. And from that, this is what you get. You are almost done. But the thing is, everyone knows that the acceleration is just the second derivative of the displacement. Yes, yes, yes. All right. So that means if I'm gonna rewrite this one in terms of x, that is going to be the second order derivative. And if I move things around a little bit, I'm just gonna keep this as a relation on the left, re-express it in the position of a sub x, then my equation look like this. So this is my triple star equation right there. So the second order derivative of x with respect to time equal to negative k over mx. All right. Just to make it a little bit cleaner, you can actually express this one as the omega, just make it a little bit cleaner. But it's not just to make things making things clean. The point is, can you solve this differential equation? That is it. This is the core of today's lecture. I'm going to take my time talking about this, even though it takes like hours, but I'm going to go very slowly because I think this is the crucial part of everything. And then I hope it will benefit you in the future as well. How can you solve this differential equation, guys? What do you think? For those of you that haven't done calculus before, this might be difficult because some of you might have done only like calculus 1. So you only do like derivatives and integration, but not like this. This is differential equation. Okay. It's a differential equation because you would like to solve for x. But now x on the right is fine, but x on the left is under differentiation. That's why we named this one differential equation. On the left is under differentiate. You need to differentiate x twice. So the way to solve this one without going through crazy calculus and all this stuff, I'm asking you very easily, guys. Think back in the past. What kind of x will it be? That once it get differentiated twice, you get itself back right here. What do you think? Okay, I'll just have you think. What kind of x, what kind of function that gets differentiated twice and you arrive back at the original one? X squared, okay, that's a good guess. Okay, all right, let's give it a shot. If you want to try x squared, once I differentiate once, okay, let me put it as an f. I do the once, you get 2x. You could do the double time, you get 2. So you won't get x squared back. Does that sounds like a good thing to sort of like a way of arriving at the final answers? So it looks like polynomial function won't work. Make sense? All right. Okay. So you get the point. Okay. Very good. So now you start to think about, John, why don't we try exponential? E to the x. You differentiate once, you get the same. You differentiate twice, you get exactly the same. So that's very good. So good. Oh, that's the wrong one. It's supposed to be happening. Okay. So that's very good. So the x squared, I'm sorry, not x squared. The exponential is the one that once you differentiate, you get the original back. Actually, you can do as many differentiation as you like. You're going to get back to itself. However, that's not this equation is. The reason I'm going to leave this one as the final question because I want you to see the importance of the sign. So this changes everything. It turns out this equation has a negative sign in the front. So that means now you have already seen that the polynomial won't work. With the negative sign, the exponential will not work either. Whoa.
Okay.
Can you see that? So here comes still the question. What kind of function, once it gets differentiated twice, gets itself back, but with the negative sign?
Hi, I'm Todd.
Yeah, very good.
Okay.
All right, so that's the whole point. It has to be sine or cosine if you want. Okay, if I write both of them side by side, derivative of sine is cosine. Derivative of cosine is negative sine. You do it twice, you get negative x. I'm sorry, negative sine x and negative cosine x. Can you see that? That's good. So it's good in the sense that now you start with the sine, you end up with the sine with the negative sign in the front. You start with the cosine, you end up with the cosine with the negative sign in the front. That's perfect. So this is the reason why the answer to this differential equation, at least it has to be in a sine cosine function. And then you now understand why you have to study sine and cosine since you were kids. And if you notice carefully, you have learned not so many form of functions. You either do polynomial, you do exponential, you do logarithmic function, you do trigonometric function, and that's it. There's nothing else to it, because those are the functions that you are going to actually need in the future, back in the day that you were kids. And that future is here right now. So this is where the trigonometric function comes into play. Okay, it's a solution to a differential equation which derived from Newton's law. Isn't that crazy? So to me, this is like a wow moment, guys. You're starting from just a simple sigma F equal to MA. You're doing just like you did, just, free body diagram, write down all the forces acting on a mass, equate that to m times acceleration. You end up with the differential equation. You want to solve for x. The solution is either sine or cosine. So it automatically gives you the solution that this mass on the spring eventually will move in the sinusoidal fashion. And that is the oscillation motion. That's it, guys. That's it for today's lecture. No, I'm just kidding. All right. So, but that's not all. The complications about this thing is, well, I mean, that's good for you. You know that it has to be sine and cosine, but can we use it? How are we going to use it? Or what is the detail about the sine and cosine? Now, you guys put more work into it. I want the full solution of this. Can you give me the full, most general solution of this equation? At least now we have a clue. It must be sine and cosine. However, you see that, Ajahn, you have a factor in the front. There is a k over m. Just only sine and cosine won't work because I cannot extract the k over m in the front. So how can we get a general solution that match, or that is a solution of this particular equation? So what the final what kind of final form of the solution should be? Can you modify this sine and cosine? The answer is, yeah, I can do that. Think about this. Every time that you differentiate, okay, let me write it down here. Sine x. You differentiate once, you get cosine. That's no big deal. But then because you want things to pop up in the front, you want some extra things in the front. So you need some extra thing in the front right here as well. Let me call it alpha for now. If you put some constant in the front, so what you are getting over here is, once you differentiate, once you get cosine alpha x, and then you do the chain rule. The chain rule will allow you to differentiate down there, and then you get extra alpha in the front. You guys with me now? And once you do it again, the cosine turns into negative sine, and then you do the chain rule one more time. You get extra alpha in the front, so it's alpha squared. You get the idea now? So this is the reason why I'm okay, Ajahn. So if you really want that, then I'm going to have to squeeze in some extra constants in front of x. And let's name that constant omega. Okay, you got that one? So if you got that one, so I'm going to do it again by naming that omega. So now you start seeing that if you start with this x equal to sine omega t, dx by dt is going to be omega cosine omega t. d2x by dt2 is going to be negative omega square sine omega t. You guys with me now? And if this is the one that you want to stick with, that's why the omega square is eventually is going to be my k over m right here. Cool. So conclusion is I can say that my omega is square root k over m. You can do everything exactly the same with the cosine function. And I can draw the final conclusion over here is you're going to get negative omega square cosine omega t. Cool? I don't know you're going to call it cool or not, but at least you see where things goes right now. It starts to shaping up what will be the final solution of this equation of motion. But that's not the end of it yet. One more time. What about if I would like to put some constant in the front of the sine and cosine function? Okay, Atan, it won't affect anything because if you look at this one, let me start using different color over here just to showcase. I can actually multiply everything by A. See that? So that means by having a constant in the front of sine and cosine function won't affect anything. You still get the original function back. So actually having the A, some constants in the front, still a solution. It works. Okay, so far so good. But that's not all. With the omega in here, I can actually add some constant inside the arguments of sine and cosine. So that means if I want to write my full solution to be a cosine omega t plus some constant phi, let's try this one together. X prime is just going to be derivative. A is A, no change. Derivative of cosine is negative sine. Omega t plus phi. And then you do the chain rule. The chain rule will give you extra omega. You guys still follow so far? I'll do it one more time. Second derivative. Negative A is there. Derivative of sine is cosine. And I do the chain rule. I get extra omega. So I'm going to get omega out. So two of them. So at the end, I'm getting negative omega square A cosine omega t plus phi. You see what I'm seeing here? You start with this. You end at this with the negative sign. Perfect. That's the perfect condition for this equation. All right. You want to differentiate twice, get the original function back with the negative sign in the front. This is perfect. So this form of function still solution. And I think this is the most general one that you can think of this sine and cosine function. With the A in the front, that means you can stretch in the vertical direction. With the phi over here, that means you can slide your function left and right. You guys with me now? I don't know, you get this form of function with me or not. I mean, just let me know if this is not sort of like it's still confusing you in any way, but that is the whole point. What I'm getting right here is just a general solution to the second order differential equation that you derived from Newton's law. Whoa. Wow. Isn't that cool? And this is simple harmonic motion, guys. That's it. Believe it or not. That's everything about simple harmonic motion. And the rest of this, we just analyze this function right here. And you should be able to understand everything that has to do with simple harmonic motion. I'm serious. Everything. Oh, I don't know. I today is good. I mean, you guys follow the whole logic over here. All right. So that's why, to me, this should sort of like stick with you until the day you die. This is it. Every time that you see this kind of equation, it doesn't have to be exactly simple harmonic motion of the mass attached to the spring. Every time that you see this form of differential equation, if it's second order, after the derivatives, you get original with the negative sign in the front, you know right away your solution has to be sine or cosine function. Okay, but now before we get further along, but Ajahn, so what do you want? You want the sine or you want the cosine? You haven't, I don't know, you have this problem or not. So what do you want? You want sine or cosine? What are you writing right now? You're writing for the cosine function, but what about the sine? Now is no difference. If you remember this, sine omega t plus 90 degree. All right. But for those of you that don't like the degree, I can do this with the pi over 2. You remember what this is? When you have a psi function and then you add 90 degree to it, what do you get? You get the cosine. On the other hand, look at this one. Then you have the phi factor in there. You got that? So if I write it one more time, if you have a cosine omega t and then you add 90 degree to it, what you're going to get? You're going to get negative sine omega t. Why not? Okay, it sounds like reasonable over here. So that means sine and cosine are actually exactly the same. It's just a translated. If you want to have a sine and then you translate 90 degree, you get cosine. And when you start with the cosine, you translate 90 degree, you get back to the sine. Something like this. So they are the same function. It's just different position. When I say different position, that is why this give you the, here we go. Wait for it, is the angular position, right? Position. And because we want to sort of like move away from geometry and things a little bit, we can call this a phase. Phase is just is an angle. But because we want to use angle to specify the position on a sine cosine type function, is a periodic function, we would like to name it phase, because with the knowledge of this factor phi over here, you can point a point. You can point a point. You can specify a point on a sinusoidal curve. Here, look at this. Hey, come with me here. Okay, just stick around. I mean, this first hour, I'm just gonna keep talking. All right, just let me know if it's like, too much. All right, look at this. Everyone knows this is, okay, let me call this f of x. I'm sorry, f of t. F of t is a, that's showing up right here, cosine. The reason that you guys know is cosine because you're starting at the peak. That's at the top. That's the characteristic of the cosine function. And you might have some omega we don't know. This one has no information. And then you can say is it at t plus 0. When I say plus 0, it means that is this point right here. Okay, you guys with me? However, if I think of this one, I don't know you guys with me or not at this point, but if I extend this curve down a bit, well, Ajahn, wait a second. The curve that I'm familiar with is this curve. Okay, let me draw this one for you. Okay, let's go slowly here. I'm afraid it's gonna be like too boring if I'm keep talking about this too much, but I think some of you might like this. All right, so if you remember, the psi function is right here. Oh, I tried to draw very symmetric one here. The psi function start from 0, 0. Yeah. Let me put the blue here. That's a 0, 0. That's a psi function. But if you think of this one, is that these two are the same point. The blue right here. So the upper curve is the same thing as the lower curve, but translated to the left. Yes, with me? Okay, so that means you can think of the bottom one. The bottom one is let me write it in a different color, the blue. F of t is a sine omega t. With me? That is just a regular psi function. Start with 0, 0. And everything just go from there. And then you go down, up, okay? That's a psi function, right? And then you say, well, I would like to get to the upper curve by starting from this bottom curve, and I'm gonna translate to the left. You guys see, yeah? Translate to the left a little bit. And then you wanna translate to the left by how much? I want the peak of this curve to be exactly right here. So it seems like I have to translate 90-degree pi over 2 to my left. And every time you want to shift a curve, you just have to adjust the parameter a little bit. So what I can do is I can do this, and I can turn this into a sine omega t. I want to translate to the left. I have to add this pi over 2. You guys with me now? And eventually with this, you end up with the cosine. So I hope I make my points right here that from now on, sine and cosine function are actually the same function. It's your preference. You can start from the sine, and then you just, play around with this argument over here. You can move things around, and then you can make your psi function appear like a cosine function. On the other hand, you can do everything in reverse. You can start everything from cosine function, and then you can move cosine function around by adjusting this parameter right here. And then you can have the cosine function appear like a sine function. So from now on, this is the reason why the solution of this, it's up to you. You can write it as a sine, or you can write it down as a cosine function. It doesn't really matter, because your general solution will look like this. So let me conclude that sometimes when you read a textbook, some textbook will say that the solution of that equation is, got it now?
Okay.
No difference. So I don't know, maybe it just my confusion back in the day that I was like studying these topics and stuff, and then I got confused. Like some book, why they use sine, some book they use cosine. I don't. Now is I hope that will clear things up. They are actually the same thing. It's just they're the same. You can slide this curve whatever you like by adjusting that phi parameter, and then you can have sine or cosine function like wave. I mean, not wave, form of the function. Up to you. Depends on the value of the phi. Okay, conclusion. This is final general solution to our second order differential equation derived from Newton's law. And this is simple harmonic motion. Woo! All right. What I'm talking today, I don't know, maybe too much. All right. However, why this one is named simple harmonic? That's the thing. Have you ever wondered what is this? Like what simple harmonic? For those of you that sort of like doing some music theory, which I don't do, there is the word harmonic over here. And then when you say harmonic, it's something related to frequency, the pitch of the sound. Okay. And this pitch is so simple. What does it mean? So I have to ask you back. Hey guys, what is the unit of omega? The constant that we introduced, and the omega square is square root k over m. What is the unit of omega? What is the unit of omega? You guys thinking, right? Not hertz. Wow, that's pretty close. Actually, it can be hertz. It's actually is right. So one thing that I would like to emphasize again, you see this argument right here? Okay, let me use different color here. Everything that follows sine or cosine or exponential or logarithm must be unitless. Remember this sort of? Yeah. We never have anything has a unit after this sine, cosine, log, exponential. So that means time is already in second. This omega must be 1/2. Must be unitless. And your friend is correct. It's hertz. 1/2 is hertz. And because in general, every time that we try to talk about the, well, SI system, everything is supposed to be like behind the sine and cosine. We use radian. So 1/2 is nothing more than just radian over second. I mean, not radian, sorry. It's sort of like the angle per second. So what we would like to talk about omega t over here, omega t, we already concluded is a phase. But the phase we already concluded is nothing more than just an angle. Okay. So that means the omega turns out to be in the unit of 1/2, but it's 1/2 in radian. So it's actually is the frequency. It's hertz. You guys, I mean, you are correct already, but it's a hertz in radian, and that is just angular frequency. You guys with me now? So actually it's the same omega that you learned before in the circular motion, 2 pi f. F is a hertz. F is a frequency, but it's a frequency in the units of revolution. Like you count it 1 cycle, 2 cycle, 3 cycles. But once you want to turn cycle into radian, you multiply by 2 pi, because every time you go one complete loop or one round, that is equivalent to 2 pi radian. So you multiply that f by 2 pi, you get the omega. All right. Under angular motion, you might name this angular velocity, but angular velocity has a unit of radian per second. It is exactly the same as angular frequency. So it's the same omega. So this is the whole point why we pick omega, because this omega eventually give you the angular frequency. So believe it or not, this formula right here already give you the angular frequency of this oscillation. So in conclusion, if you have a mass attached to a spring that has a constant spring constant K, it will oscillate with the angular frequency of root K over M. Seriously. Yes. Yes. Okay. So let me give you a quick example. If I have a mass of 1 kilogram, okay, and then I have a spring that has a spring constant of 100 Newton per meter, and then I attach the spring to this mass and let it oscillate, you can calculate the angular frequency to be square root K over M, and that is just root 100 over 1, and that is 10 radian per second. Seriously. That's it. It's going to go bow, 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 10 radian per second. And if you want to find the frequency in terms of hertz, you just divide it by 2 pi. But that's what it is. It means it doesn't matter. You attach it with whatever numbers, whatever, as long as you have this mass with this spring, is going to oscillate with this frequency. Cannot change. That's it. All right. So that's the key point. So in conclusion, the omega is angular frequency. So let me write it down here. Omega is 2 pi f. But then the f frequency, you guys know, is just the inverse of period. F is the cycle per second. If you flip it over, it's the second per cycle. So that is your period right there. So there's no doubt. I put a quick formula over here. The omega that you are seeing is just the 2 pi over period of that oscillation. So the period of oscillation is the time that it takes to complete one full round. So wherever you start, you go and then come back to complete one cycle. The time that it takes, that is called one period. You take that period, divide it out, the 2 pi, you get the omega. All right, sounds good. All right, there's a question, what if spring deform? All right, don't think too much. As long as you use this equation here, so we assume that is following Hooke's law. Okay, so that means you still assume that there's no spring deformation. All right, if the spring is already deformed, it's not going to follow this simple linear equation, so it's not going to be simple harmonic anymore. Okay, that's a good question. Yeah, actually, is in a real spring is not going to be following Hooke's law 100%. It has some, variation there. Okay, all right. So I hope, I don't know what kind of things that you are seeing at this point, but I hope you get the grand pictures of what I'm trying to explain. And well, it's a lot of talking, but it seems to me if you sort of like going back and forth between the original starting point of the second order differential equation and the final form of the solution, and then you just sort of like staring at it, just keep staring at it. What is the starting point? What is the end point? What the end point is trying to say, and then you go back to the starting point. What is the starting point is from? You go back and forth, give it like a few hours of this one, and then you eventually understand what the simple harmonic motion is. That's my take on it. I don't know. It's better than just read like the whole textbook and then try to understand what this is. But it seems like it's better for you to spend time with yourself, trying to understand what this is. So what are omega and F again? Okay, so omega, we conclude that because it's the factor in front of T, right here. So we know that now the omega must have the unit of 1 over, unit is going to be radians per second. Okay. All right, so now the omega is going to be angular frequency. Okay, with me? So it's a frequency in the units of radian. And the F itself, just the F alone, is just frequency. So for the frequency, that is the revolution per second. And this one, you can name it hertz right there. Okay, so the relationship between the F and the omega is 2 pi F. So you just take the regular hertz, the frequency, rounds per second, revolution per second, multiply by 2 pi, because each round equal to 2 pi radian, you can convert F into omega. This formula to me is just a units conversion. It's not a formula or anything. It's just you want to convert units from round revolution into radian. So that's you multiply by 2 pi. Okay, does that answer your question here? Okay, all right. So, well, I spent the whole period here talking about the simple harmonic motion, but I hope this is the key. I don't know what else is the key. If you want to talk about the key, this is the key. All right, and this is the conclusion, guys. And I think it's good place to take a break right here. But during the break, for those of you that are sort of like keen to look at what is going on, this is the final conclusion. On the right, that give you the whole semi-animation of what is going on with the oscillation of the mass on spring. On the left, we start from the most general form of our solution is A cosine omega t plus phi. And now you know is your choice. You can start with A sine omega t plus phi as well if you like, but that means the same thing. And we will start from this and derive everything else, speed, acceleration, whatever, and try to interpret what this A, omega, phi, and everything means one more time after the break. Sounds good? Okay.
Okay.
All right. So let's take a break right here and then we'll meet again, let's say 11, and then we'll dive down into this. Okay. All right. All right. Okay. So what we are going to do next is once we have this, the reason that why I am so sort of like focused on this so much, because once you have this down, you know everything about this motion and this is it. It's done. This motion has already been described fully. The reason I say fully because once you know x as a function of time, if you ask me about Jan, what is the speed, what is the velocity of this, all you need to do is just take derivative of x with respect to time. You get to velocity. Once you get to velocity, you do it one more derivative. You will get to the acceleration. So that means you can describe the motion every time, everywhere, wherever, whenever, whatever you want. It's done. Okay, so let's take a look at the detail of what this means one more time. So if you look carefully on this one, because everyone knows that the cosine function will never go beyond negative or positive one, correct? So that means with the factor a in the front, so it says that x supposed to run between negative a to positive a. Yeah, that's the value of the x. So that's why we say that the a will actually give you the maximum possible value of x. And we name this one amplitude. Perfect. So it has the amplitude of the motion. This oscillation has the amplitude. That's where the A lies. So once you do the differentiation, you take derivative of cosine, you get negative sine. Do the chain rule one time, you get extra omega in the front. You can still do the same interpretation over here. If you look at this one, then you can see that A omega is in the front. And that will give you the maximum possible value of this function anyway. So that means the A times omega will give you the maximum velocity magnitude. So that's why we call omega A V max. You start to see the trend now. And if you do the derivative one more time to get to the acceleration, derivative of sine, you get cosine. And then you get negative. I mean, you won't have any negative anymore. So that's original negative sign there. You do one more chain rule, you get extra omega. So you get omega square in the front. And the A omega square will be the maximum possible value of the acceleration. So that will be your maximum acceleration anyway. So good. Okay, so now you understand what does it means by the factor in the front of sine or cosine function. It's just the maximum value. And if it's a maximum value of the displacement, we name it amplitude. Other than that, it's just a maximum speed or maximum acceleration. Okay, sounds good. All right, and if you look at this one, the cool thing about this one is now you can adjust your parameter phi wherever you want. However, if you look at this figure right here, you see that you would like to start everything from the amplitude. This is where you want to start everything. It's like you stretch the spring all the way to the maximum displacement that you want and you let it go. So that means at time 0, the x is at amplitude. You guys with me? So if this is the case, the phi that you pick in this movement over here is phi equal to 0 because you start everything from amplitude. Okay, you guys sort of see the utilization of the phi. But sometimes your friends might just walk in, but Ajahn, I don't want to start my time 0 here. You want to start somewhere else. You want to start from the equilibrium point. You want to start from, now you can adjust this phi parameter. So sometimes this parameter can be named, or you can sort of call it the initial phase, because that's allow you to start your analysis at anywhere you like on the sine and cosine function. Does that make sense? All right. So that means if you come back here, you can start your time 0 here, or you can start right there. You can start right here. You can start from here. You can start from wherever you want. You can pick your position that you want to start everything. So that's why phi can be treated as your initial position. But the position in angle, you name it the phase. So that's why we name it initial phase. Okay, cool. All right. So in this particular case, I mean, if it's going to describe the movement on the right, all I need to do is just pick phi to be 0. And this is what you get after it. Okay, sounds good? All right, just to make things a little bit better, learning this oscillation things, it seems very boring if you look at just like a static images or just static photo figure over here. So I think it's better for you to actually go online and try to take a look at the simulation. I think that would be the best. All right, so I will send you a simulation that you can actually take a look at the change and the curve, and I think we can look at this thing together. That would be nice, I think. Okay, so I have actually, you can search a simple harmonic motion simulation and things like that, and that should work. All right, I'm sending it to you now. You guys can try that. I think we can do it together here. So let's do that. So let's do what? Oh, physics. Okay. .com. I should have done the search myself. It's a w1.html. Okay. There you go. There you go. All right. So it's a simple harmonic motion mass on spring. This is very good. And it used like GeoGebra engine. So it's supposed to be good. So over here, all right, just to make things a little bit cleaner on this one. Okay, let me sort of uncheck these boxes over here because we don't need it now. Don't need the numerical value. And this is things to happen. So let's move things slowly here. Okay, and as you can see, you can adjust your initial stretch. See that? Okay, so we assume that, okay, let me stretch all the way out. And then you can adjust the mass of this one, and it's good that it's changing the size of the mass to reflect that magnitude of the mass. And the spring, you can change the stiffness of the spring. You can see that when you increase the K, the spring look a little bit thicker. So it's make that sense of like it's more stiff. The spring is sort of like hard. It's gonna bounce pretty quickly. And if you make it light, then it's gonna be like sort of like a soft spring. So it's gonna move very slowly. So as you can see, the K will affect the omega. The M will affect the omega because we know the omega is a square root K over M. So we can test it now and take a run to it. Okay. All right, maybe. Yeah, and then now you can play around with this and then you can just watch the curve on the right that is plotting, and it's plotting everything starting from the top. That's the displacement. And as you can see, the curve on the top starting from the maximum value, because you're starting everything from the amplitude, right? And things start to go down and then passing 0, go to the -1, and then go to the largest value of the negative side, and then reverse the direction and go up again. All right. And as you can see, the velocity is going to be a 90-degree difference in terms of the shape of this, because if you look here, see that? The derivative is always a slope. So at whatever the slope of the orange curve is going to be the value of the blue. And if you do the slope of the blue, you will get the value of the purple. And as a relation. Sounds good? All right. So all these curve has to connect because they are related through derivatives. So there's no doubt why the curve look like they are shift a little bit. That's what it's supposed to be. All right. I can make the speed a little faster. Okay. All right. Let's reset and run again. All right. You guys can play this around at home if you wanting to do that. I mean, that will be fun. And then you can adjust the parameter K and M just to see like, hey, what is the change in the omega? And then you start to see that if you have a very big K, small m, it's going to bounce back and forth very quickly. And if you have like a big M, small K, it's going to so slowly oscillating. Okay, sounds like, all right, so this time, I mean, in terms of like having some animation at home to try.
Okay.
All right, don't forget to do some relationship and all this stuff. That's supposed to be helpful, I hope. All right. So with that in mind, now we can come back and pretty much understand everything else by trying this, guys. One more time. All right. If you get to this and then you know how to deal with this, then I think that's accomplished my goal today. You understand what the simple harmonic means. But we started from a simple system, mass on spring. So let's try this one. Okay. How do you feel? What do you think? Now I have a pendulum, a simple pendulum. So what I'm going to show you is, if I would like to start the same thing, I'm going to use Newton's law, the second law that we use, sigma F equal to ma, and try to write down the equation. I should end up with the equation of motion, right? So let's draw a free body diagram one more time. I have mg down here. I have tension pulling up. This is just a simple pendulum, right? That's a mass hanging from the ceiling with a light string. And then because the movement is going to be in the tangential direction over here, so what I'm going to do is I'm going to decompose my vector into the direction that is parallel to my dashed red line over there and perpendicular to it. So I have mg cosine theta down here, and I have mg sine theta back here. Cool. And the vertical direction, I don't have to care about it because the mass won't travel up and down along the string. It's going to travel along the tangential line. So what I'm looking at is I'm looking at it right now along this direction right here. So we can call it S at this point. Okay, because it's not X, it's not Y, it's just curve, but that's okay. Just call it S, some displacement along the curve path. Okay, so what is going to be my equation of motion? You say, well, no big deal. Sigma F equal to ma, but you only have one F right now, is the mg sine theta. But this mg sine theta, look at this one. Now the S is the displacement, right? But the displacement is along this curve right here. So let me draw it like this. You're going out all the way here to the right. That is your positive direction. But now your mg sine theta actually it's pointing backward. Mg sine theta, let me put it in the green. See that? So the mg sine theta actually pointing backward while the S is at the positive position. So that's why I need a negative sign in the front. Mg sine theta with a negative sign equal to ma, but a is just a tangential acceleration. It's an acceleration along this curve. It's still second derivative of s with respect to time anyway. Cool? So far so good? All right. Okay. Now, I'm just going to rearrange the equation a little bit, guys, just for fun. M cancel. So this one is clear that the simple harmonic, the pendulum is going to oscillating without any influence from the mass. So that means no matter what mass you are using in this pendulum, you're going to get exact same oscillation. You guys with me? I think you have heard of this one already. So that's good. Second thing is I'm going to do just like what we did. I'm going to try to write this acceleration as something else. d2s by dt2 equal to negative g sine theta. Whoa. Can you solve this equation? It's the second order differential equation one more time. But, well, Ajahn, that's kind of bad because you have S on the left, you have theta on the right. What do you want to do with this? Because they are different parameters, different variables. I can relate them because if you look at this, I can look at this. Here we go. You can look at this portion of the circle or it's not triangle. Okay, over here. All right. And when you look at this one, you say, okay, I can draw the relationship between the angle that it makes with the vertical line, the theta, and the S, the arc length along this path. And we know that the theta, we know that the theta by definition is just the arc length divided by the radius. You guys with me? All right. And now here's the key. But Ajahn, you have the sine theta. You don't have the theta. And this is the approximation that I'm going to bring in.
Okay.
When the theta is small, sine theta is approximately equal to theta.
Okay.
I don't know, have you seen this before? But we will use this again later. But this is a good thing is actually tan theta works the same way. All right. And this one is sort of makes sense because when the theta is small, you don't really care, is this going to be an part of the arc or is this going to be like a full triangle? It doesn't really matter. Okay. So you can treat this one as a right triangle, or you can treat this one as just a section from a circle. Doesn't matter. So when the theta is small, then you can approximate that it's going to be approximately equal to the theta itself in the radian unit, of course. Okay, you can punch the calculator and test. All right, so if you punch like sine 0.01, it's going to be approximately equal to 0.01, pretty close. Okay, so that's why if you, and for those of you that remember vaguely, if you study physics about this topic, about the pendulum back in high school, they usually say that the oscillation has to happen when the angle of oscillation is less than 10 degrees or something like that. That 10 degrees restriction is just for you to be able to do this approximation. All right, so we assume that the approximation works. So I'm going to write it as about G theta. And the theta is just S over L. You start seeing something now? If not, let me write it one more time, guys. D2S by dt2 equal to negative G over L S.
Okay.
Start seeing something now? Yes or no? Yes or no? And this is what I'm trying to say. From now on, I mean, from then, the first time that you saw the second order derivatives, now you see it again in front of you, but look at the structure of this one. How do you feel? Say, I want you to stare at it. How do you feel? Yeah, it's similar. The reason it's similar because you can see that what you are looking at is, hey, what is the S that once it gets differentiated twice, gets itself back with the negative sign? But okay, John, it's sine and cosine. And you still need some extra factor in the front, but that's okay, John. I'm gonna name this extra factor my omega square. Can you see it now? It's the same structure. So with that same structure, I don't need to do anything anymore. What I can do is just like, okay, let's name this G over L to be my omega square. And I can write down the solution. Let me write together with you guys. I can write down the solution right now. S, let's use the black here. S as a function of time is going to be, can you guess? Amplitude, sine or cosine, your pick, omega t plus phi. And that's it. I'm done.
Okay.
Isn't that cool? And I can tell the omega that you're going to squeeze in here is just square root G over L. So what I'm saying over here is whenever you have a mass on spring or pendulum, in this case, now we're looking at the pendulum. I don't know, can you see this or not? So as long as you having the same value of the G and the length of the string that you use is fixed, this pendulum is going to oscillate back and forth with the same frequency. The only way that you can change the frequency of this oscillation is either you change the length of the string or you go to some other planet, change the G. All right. You do it outer space or whatever, underneath the earth or whatever. You have to change the G for this pendulum to change the frequency of oscillation. Isn't that cool? So this is why back in the day, they can use the pendulum to be a mechanical clock. So you can use the frequency of that oscillation to treat like a 1 second, and then you use this as to be a mechanical clock, and based on the frequency oscillation, you can call, okay, 1 second, 2 seconds, 3 seconds. So it's a pendulum clock back in the day. Okay. All right. Sounds good. So this is what it is. And I mean, the mathematics of the day is now you understand this form of differential equations. And from now on, wherever you see this, you don't even have to solve these equations anymore. You can just say right away about Jan, it's simple harmonic. Solution is sine and cosine. I know the omega is going to be the square root of whatever the thing that is in front of this variable that you want to solve. And done. Isn't that cool? All right. So with that, this gives you the approximation that I was talking about. Okay. And it's pretty good up to about, as you can see, about 10 degree. It's getting, well, it's pretty close. Yeah. The error is still within less than 1%. So that's why if you have the oscillation is about 10 degree, the simple harmonic motion can be treated. You can treat the simple pendulum to be simple harmonic motion. But now you know, if you swing things with a very high angle, that oscillation is no more simple harmonic. Isn't that crazy? All right, so that's good to know, good to know. But for us, I mean, simple harmonic is good. It's always good. All right, now let's do it one more time, shall we? And this one, I'm gonna take you to something realistic. What if you have some physical stuff? It's not just like a mass on a spring or just a pendulum, a mass attached to a spring anymore. But now you have like a stuff like your hands, your legs, your body, the car, the object, the box, whatever. And you sort of like hang it on something and then you want it to swing back and forth. So you can try to calculate the oscillation of that as well by start with the equation of motion again. Can you do it? I don't know. Have you done this back in the, I don't done this, not exactly this, but have you write down the equation of motion of this kind of object back in physics 1, maybe? Okay, maybe not. All right, that's okay. All right, now you have a physical object over here. You have a pivot. So you somehow sort of like hinge it on this pivot point O. So this mass over here can sort of move freely around that point. Okay, so now you start having some circular motion there. And then you see that the CM, this one is at the distance D from that pivot point. Okay, and you would like to write down the equation of motion of this. What are you going to do? You're going to use the Newton's law again, but now it's the second law in the form of circular motion or angular motion. You remember that? What you use is total torque equal to I alpha. Does it look familiar to you? Yeah. Okay. So now instead of sigma F equal to MA, you do the sigma torque equal to the moment of inertia times the angular acceleration. It's the same form anyway. It's the Newton's second law for angular motion. You guys kind of quiet, but I hope it works. Okay, so what we have over here is now I would like to talk about the net torque. Look at the mg. That's the only force that's acting on this mass right now. There's nothing else. So if you are talking about the motion around the pivot points, okay, the mg will generate a clockwise rotation. So this mg will try to bring this mass, turn it clockwise direction. Use your right hand, forefinger, wrap around this. Your thumb will point into the screen. So that means this mg will generate a torque point into the page. So let me call this torque into the page. I use the cross symbol. Okay, make sense? Now, at this particular point, if you look at the theta here, the theta is the measurement with respect to, what is going on? What's going on here? The theta is the measurement of the position with respect to the vertical line right there. If you rotate your forefinger along the direction of the theta, right now the theta is pointing counterclockwise, okay, counterclockwise. So you roll your forefinger, your thumb will point to your face, perpendicular out of the screen, out of the page. So actually the theta right now is pointing to you out of the page. So that is the sense of the direction. If you want to call something that point to your face to be the positive z direction, so you can name this as a positive z. So the mg will have the torque pointing in the negative z direction. So the torque due to the mg is in the negative z direction. You guys with me? Okay.
Okay.
And now I'm going to apply Newton's law in the angular motion here. So the net torque is going to be mg times the distance from the, we need more 3D picture. No, don't need. So the torque is the distance from, force. Okay, let me write it like this. Torque is R cross F. And it's just RF sine theta, right? So over here is by definition of the torque is just the force multiplied by the distance from the line of force to the point of, you say the axis of rotation, or in this case, it's our pivot point. Oh, so what you have over here is you can extend this line of force over here. It's this vertical direction over here. And the distance that you would like to calculate is this distance right here. And that is the d sine theta. Sounds good? All right. You remember how to calculate torque a little bit? If not, that is okay. All right. That's not the big thing that we want right now. But at least for those of you that still remember how to calculate torque. So the torque due to the mg is going to be mg d sine theta. That is a torque. Okay. Let me write it close to this. Let me bring it here. There you go. There. Okay. However, it's pointing into the page. So that's why I'm arriving at the negative mgd sine theta. There is a negative sign in the front because this torque is pointing into the page. And now I just equate that to the I alpha because I don't have any other torques applying onto this mass anymore. So I is right there. Alpha is just a second derivative of the angle with respect to time because right now angle is positive. So this is good. Does it look nice? Cool. Now you start to see that, can you solve this equation now? Almost. But almost, except this annoying sine theta. But we had no problem before. Now we're going to have no problem now. I can approximate this one to be theta when the angle is not that big. So my equation will look like d2. Okay, let me do it in step here. Negative mg d theta equal to I d2 theta by dt2, yeah? And now it's sweet. So I can rearrange the term. I can put my d2 theta by dt2 on one side and move everything to the other side. And now you like this? Can you see it? Yes?
Okay.
What you are seeing over here is the pattern again. You have the theta that you want to solve. You differentiate it twice. You get the original form function back with the negative sign. Whatever in the front, you're going to name this omega square. It's right here. And you don't even have to do anything. I can write down the final solution of this one is the angle as a function of time is going to be some amplitude, sine or cosine, your pick, omega t plus phi. And I'm done.
Okay.
Isn't that cool? All right. So I hope you see what does it mean by simple harmonic motion. It happens everywhere in this universe. No, that's boy. The thing is, wherever you hit this form of the equation, mass on the spring, simple pendulum, this one you can name it a physical pendulum, any crazy system that eventually you can write their structure, equation of motion, and you ends up with this form, they will all oscillate. And then once you can pin the form of the factor in the front over here, you will also know its angular frequency automatically. So you know exactly what kind of oscillation frequency it's going to get. And because one system, you're going to get one omega. This omega eventually will lead you to something that we name natural frequency. The reason it's called natural frequency because you cannot change it. Once you have a system, it's going to oscillate at this frequency, unchanged, until you adjust the system itself, like change the mass, change the spring, change the planets that you're doing pendulum, change the moment of inertia of the stuff. However, once you fix these parameters, the system will oscillate at a single natural frequency, unchanged. And you know exactly what kind of equation it's going to get. Yeah, sine or cosine. That's the importance of this trigonometric function. Believe it or not. Whoa.
Okay.
Okay, sounds cool. So I hope I have already shown you the whole structure of simple harmonic motion. It doesn't have to be these three systems. It can be any systems that has this structure of the second order differential equation. You will get simple harmonic motion, period. And you know how to write the final equation right away, right away. Can it be gyroscope? No, gyroscope is not oscillating. So gyroscope is just a three-dimensional rotation. So it's not oscillations. So the key of this one is it needs periodic motion. It's go back and forth, back and forth, back and forth. But the gyroscope actually has some, how can I say? It's almost the same as you have trigonometric function right here. The trigonometric function is a periodic function as well. So every time that you have a circular motion, that's no doubt why you have to deal with the sine and cosine, because it's a periodic as well. But for us at this point, is going to be some mechanical stuff that bring this system into oscillation. And if you notice everything that we have done from the beginning, see this? Minus kx, okay, minus kx. Next, minus mg sine. See that? I don't know, zooming in and out is gonna like make you dizzy over here. Minus mgd sine theta, the torque. As you can see, these three systems have the same thing going on here. Is it has something that has to restore the position of the movement. We name this a restoring force or torque, depends on the thing. So you need something to pull the system back to the equilibrium positions. Okay. Sounds good. All right. So over here, you have the torque. When you pull the mass or this object a little bit away from the equilibrium position, let it go, the weight of the mass try to pull things back to the equilibrium point. That's a restoring torque or restoring force. Spring, when you pull it, stretch it out, the force from the spring try to pull everything back to the equilibrium point, something like this. All right, so this is a structure of the simple harmonic motion. There must have some underlying force trying to pull things back to its original equilibrium points all the time. Okay, what is I again? Okay, I is moment of inertia. I don't know you remember this or not, moment of inertia. So for a simple form of this, it's going to be mass times the distance square. I don't know, have you sort of recognized this? No? All right, don't worry about it. If not, that's all right. Let's say that sigma F equal to MA. The mass is the inertia to the motion, right? It doesn't want to translate. The larger the mass, the object is sort of like inert to the change of the movement. The I will do the same thing, but is the inert, this is inertia, right? It's inert to the rotation. So things that has a very big moment of inertia, it will be harder for you to turn it. The things that has a big mass, it's harder for you to push it. Bigger mass, you push it. I mean, it's going to be difficult for you to push it to move. The big I object, it will take you a lot of work for you to turn it because it's so inert to your angular movement. Does that make sense? Okay. So
Okay.
M is the inertia to the translation. I is the inertia to the angular motion, twisting, turning. Okay, something like that. All right. Okay, cool. So with that, so it seems like I'm done with describing the motion that is oscillating. We name it simple harmonic motion, and it's sinusoidal in nature because it has to have a periodic movement. So at the end, because you know the displacement, you know the velocity at any time, there's no doubt I can ask you about the energy. Well, hey guys, what is the energy during this oscillation? Oh, that's easy. The energy that you have is either in kinetic energy form or is either in the potential form. What else do you have? So about Ajahn, that's no big deal. The kinetic energy is 1/2 mv square. The in case of mass over spring, it's just 1/2 kx square. That is for spring elastic potential energy. So if you want a total energy, all you need to do is just sum them up. But then because we know all the information, the x is a cosine omega t plus phi, so you just square them. The velocity is just, we already saw it, omega a sine omega t plus phi, you square them, and just add them up. So far, so good. All right, so I mean, all you're doing is just go back to this one. You take this x, you square it, multiply by 1/2 k. The velocity, you take this, you square it, you multiply by 1/2 m to get to the kinetic energy. So once you have those, and then, oh, that's kind of nice then, because we have the relationship that omega square is k over m. So it depends on how you want to turn. I mean, I can change omega in terms of, I mean, write it down as k over m if I want to. So I can rewrite k over m in terms of the omega square. So you have a common factor of ka square. And what you have left here is the sine square plus cosine square, and it's just 1. That's from the trigonometric identity. So at the end, whenever you try to calculate the net energy of the system, is always 1/2 ka squared. Oh, you got that one? It has to be because of what? Because at the starting point, yeah, look at this one. Let me reset this. Okay, you start right here. See, you stretch the mass out. At the moment of the stretching, you already has a potential energy in it equal to what? 1/2 ka squared. And you let it go, run, bam. Of course, part of that potential energy will turn into kinetic energy. That's why the mass starts to move faster and faster. But when it gets into the other end, it stopped. It converts the kinetic energy back to elastic potential energy, and it's going to get pushed back. So there is a conversion back from potential back to kinetic, kinetic back to potential, potential back to kinetic, on and on. So it's an oscillation of the form of the energy as well. But no matter what form that the energy is having at the moment, the sum of the energy must be equal to the initial energy that you started out with, 1/2 ka squared. Okay, got that one?
Okay.
All right, so it's no big deal. So that means what you see over here is I can show you the energy curve now. All right, and I can go slower so you guys can pick up this one a little bit faster. Oh, I have to pause it first, I guess. All right, here we go. Reset, try again. There you go. See that? So now when you start from the highest potential, but then when the mass starts to move, you convert part of that potential into kinetic. So that's why the mass travel a little bit faster, until it's going to get the fastest at the equilibrium position. When it's past the equilibrium position, it will get slower and slower, and the kinetic energy turns back into potential energy. And this oscillation is just go back and forth, back and forth. But if you look at the black line over here, okay, that's the total mechanical energy. The word that they say ME right there, the mechanical energy net total has to be the same. The black line just flat. So the sum between K and U at any time must be always equal to total mechanical energy, the black line right there. Okay, sounds good.
Okay.
It's kind of fun learning this. I don't know. I know it's a lot of mathematics over here, but the good thing is you only need like derivatives to understand this. There's no integration or anything to bother you. And I think the complications about this one is about you have to understand sine and cosine function very well, so it won't get annoying in the future. And you have to understand the similarity between the sine and cosine. I think maybe that helps. Okay. And once you understand all this stuff, everything else seems to be pretty much same pattern. I would say they're sharing the same pattern. So that's why understanding one thing allow you to understand everything. Nice. Okay, cool. Sounds like a good one today. I don't know. All right. Okay, so that's a good thing about knowing positions at any time lead you to velocity calculations, acceleration. Once you know all the positions and velocity, you can calculate the net energy at any time. Okay, and that gives you the energy during the simple harmonic oscillation. Sounds good? All right, and that's conclusion that you have right there. Okay, all right, so it's conversion back and forth. What else should we try? I think last page, guys. I think we're almost done. All right, so anything that you want to ask at this point? But in real world, we don't know every value at t. Yeah, actually we know, because this is not too bad. It's not that complicated. For example, for the spring, you know how much you stretch. Let's say you stretch the spring by 5 centimeters. Yeah, you know exactly. And then you can calculate the potential energy exactly at that point. So that's not too bad. For this simple mechanical oscillation, you know all the information. Yes. Okay. All right. So I think this is the point that I want to make. But I would like to attach the last slide of the day so you get some connections to the realistic application. All right. But we don't do any calculation on that. So let's look at the last page about the oscillations. We named this damped oscillations. The reason this one is damped because we would like to mimic the situation where you have a friction in the movement, where you have some here resistance. So for example, if you have mass on spring, but then the mass itself is pretty much on something or in something that can create frictions or resistance, your equation of motion will change a little bit. Look at this. Sigma F now is not going to be only just the spring's force, but you're going to have some sort of like a resistance term built into it. And one terms that they are pretty much interested in is the resistance that is proportional to the speed or the velocity of the mass. And this makes this equation looks now complicated. And then you need to know how to solve this one using some calculus. You might have to do like some, I don't know, integrating factors, all this stuff. But the key is, I mean, calculus will show you how to solve this one, but that's not our point. Our point is this. You kind of get a sense of what's supposed to happen when the mass has resistance into it. Can you guess what will happen? No, Ajahn, well, we're not going to solve this, but we know it's going to look like this. It's going to oscillate, but everyone knows that the amplitude of the oscillation will get smaller and smaller and smaller and smaller and smaller, right, until it dies down. That makes sense? Because the friction will take away all the energy eventually. So we know that the amplitude will decrease over time. However, if you agree with the resistance that relates to the speed in this form, so it means the resistance is linearly proportional to the speed of the mass, it turns out we know the characteristic of that decrease. It turns out to be exponential decay. Whoa. All right, but we don't care. All right, don't worry about it. That's not the point. The point of this slide is this, but Ajahn, wait a second. How can you sure that you are guaranteed to get some oscillation? Oh,
Okay.
what does it mean? It means, look at this one. If you put the mass into a water, for example, and then you pull the mass down, let it go, it's going to try to oscillate, right? Maybe in water, you still fine. If the spring is stiff enough, then you see oscillation, and then it's going to go bow, 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 bow. Eventually, it's going to stop. I mean, the frequency shouldn't increase. Right? It's going to, and then eventually it's going to die down. Everything is fine. Looks okay. But now, if you change the water into, for example, maybe honey, or something is so thick, super thick, and then you pull the mass down, let it go. It might not want to go anymore because it's so thick. It might just like, you start, it doesn't want to go. There's no oscillation behavior. Industrial grade glue. If it's a glue, maybe it's already stuck right away. It doesn't show up. So that's the key too. So it depends on the environment that the mass is in. It depends on the magnitude of the resistance. Sometimes the resistance is way too high, so you won't see any oscillation whatsoever. And that can be classified into two types of oscillation. So over here, if you still have the environment that still allow the oscillation to happen, you call it an underdamped oscillation. This is good. You can still see some oscillation with the decreasing amplitude. So this is fine. The flex tape. All right, that's kind of like the glue the tape. I think that's too much. That's all right. That would be no more movement. All right, but then if you grease, okay, let's say the grease or something like super thick, you know, crystalline and all that stuff. So this one will go for the overdamp. So this is too much. So you wouldn't say there's any oscillation anymore because once you let it go, it's just, it doesn't want to go anywhere. All right, so this is overdamped. But the good thing, well, not the good thing, but the most interesting thing is happening here. There will be a boundary between the two. You can, let's say, if you can tune the parameter of that viscosity, let's say if you can tune the viscosity of that liquid from a very light to a very thick liquid, then there will be a borderline between jumping from underdamped to overdamp. Make sense? Let's say if I increase the viscosity, there will be a line that this oscillation will cross from underdamped to overdamped. This one, we call it the critically, oh, that's only one T there, sorry. It's critically damped oscillation. Okay, so the red lines tell, why don't I do the color coded here? Sorry. All right, so the red line, that was the one that is the boundary between the over and under damped oscillation. But do you notice the behavior of these three curves here? If your goal is trying to get to the equilibrium point, the black line is bad because it would take a long time for the system to approach the equilibrium. The blue is kind of like bad because it's undershoot, overshoot, undershoot, overshoot before it gets to the equilibrium point. But do you see the red line here? Whoa, this is so good. It will actually approach the equilibrium point very efficiently. And that's how engineers design the pneumatic, or I don't know, whatever the choke up, the coil, the spring, whatever the things that try to put it in the car, in anything that's try to suppress the oscillation and all this stuff. They try to tune it to have the physical parameter sit right at the critical damped oscillation. Sounds good? Yeah, so that will give you the most efficient way for things to get back to the equilibrium points. So when you have like a like the door, for example, like hydraulic door. So when you open the door and let it go back, I mean, if the hydraulic system is bad, the door will swing back and forth until it stops moving. So that's bad. That's underdamped. But if you have a hydraulic system for the door to be too stiff, once you open the door, you let it go, it would take forever for the door to close down. That's bad. But then if you tune the hinge, that hydraulic system hinge, to be in a perfect tuning position, once you open the door, let it go, it will close the quickest.
Okay.
I don't know what that link to the real world application, but that's what it is. All right. So that's the shock up in the car, the spring system, the whatever the things that try to help supporting stuff and then try to slow down or decrease the oscillation and the stuff. They try to tune it at the critical damped oscillation parameters. If that's, I mean, relate you to something close by. I hope. Soundproof wall. Well, soundproof wall, that's kind of, I have some sense of it. Yeah. But even though it's not so obvious, but because the sound is oscillation in the molecular level, so you probably don't need to tune that much. For the soundproof, you need to absorb everything. So it's more like an absorption thing. So you want things to get absorbed. So you might not care much about how fast it get absorbed because it's a molecular levels stuff. But yeah, but it has some connections to this. Okay, guys, I think that is it for today's lecture. I hope you learned something. I don't know, maybe I talked too much today, but next time we'll do more numerical calculations than today's. But I hope you learn the it's simple harmonic motion in a nutshell today, I think. All right, and next time we'll get connections to the waves. It will get more complicated. This one is sort of like an introduction to that. All right, and what is going to be, that's until next time, guys. All right, I'll see you on Wednesday. Yeah. All right, bye-bye.